So let's start. I'm back. All right. So just a reminder that after this session, there's another sort of problem-solving session. So we'll have handouts with problems on them to work on in groups, and that'll start sort of roughly pretty much from whenever this talk ends until 1:30 when it's time to go, hop on the bus, and so we'll have a chance to think about some of the concepts that have sort of come up in the talks both yesterday and this morning. One other point is the talks I have. Sorry, the things got rearranged a little bit. So the talk I'll give doesn't correspond to the slides you have printed. The slides you have printed are for tomorrow afternoon. That's my fault. I sent the wrong file to Yonit. My understanding is these are on the website or will be momentarily, so you can get if you want, you can get a PDF version, during the talk. They're on the website for the winter school, but you can also just, follow along as I talk. Okay, so I'll be talking about the local model for differential privacy. So far, we've by and large been talking about sort of the following picture. We've got an algorithm that collects a bunch of data from individuals and then processes it. It's a randomized algorithm, so it has its own local random coins, and then it spits out some output. Maybe it answers queries in some interactive way. But in particular, we have a trusted curator that's holding all the data. Okay, in the local model, we have a very different picture. So in the local model, it's a special case of this original picture where the algorithm that is processing the data has the following additional structure, which is that each person is feeding their data point into some sort of little algorithm that's doing the randomization for that person, and that's talking to some centralized aggregator. But the key distinction is we don't trust the aggregator to handle sensitive data privately. And so all the randomization is happening at the level of these individual little boxes that we'll call the QIs, or sometimes we'll use the letter R for them. The advantage of this model is that we can think of the QI as running locally on a device owned by the person whose data it is randomizing. Okay, so for example, that could be your cell phone, or it could be your computer, or it could be. It could also be that this process is being run for you by some central algorithm, but it need not be. Okay, so in this model, the requirement we need in order for the whole process to be differentially private, what we need is that each individual little box that's randomizing a given person's information should itself be epsilon delta differentially private. Again, if each of the QIs is epsilon delta differentially private, then the whole algorithm will be epsilon delta differentially private, and that's because each person is only talking to one of these little QIs. Okay. Now, for the talk, I'll ignore the role of delta, so we're going to be talking about epsilon 0 differential privacy for this entire. I'll be talking about epsilon 0 differential privacy for this entire talk. One of the nice things is that's essentially without loss of generality in this local model. So in this local model, one can argue that the delta doesn't really buy you anything, unlike in the central model where it makes a huge difference, or can make a huge difference. Okay, just some extra notes on the model. It's fine if the aggregator kind of goes back and forth and talks to each person multiple times. And in particular, it's fine if the aggregator provides some input to each person. So the aggregator could say, please run the following little Q algorithm for me, right? So the aggregator could have some say on what this randomization operator looks like. That's fine. That's not going to affect the privacy guarantees. So again, all we want is that at the level of each individual box, for every pair of values that person I's data could have, and for all events T, the probability of that event when the person's data is X and the probability of that event when the person's data is Y, these probabilities should be closely related. Okay, so the advantages of this model is precisely the fact that you remove the need for a trusted curator, right? So that means, in particular, it removes this sort of single point of failure for security properties, because now you're sort of relying on these individual little boxes being doing the randomization correctly. And also in terms of efficiency, it can have some advantages in terms of just distributing the computation over a large set of processors rather than having everything living in one place. Yeah, there was a question. No. That is, I mean, maybe one can. I don't, off the top of my head. The question is, why doesn't delta matter in these? Why doesn't delta significantly change the definition here? And I don't have a, maybe when we get to information theoretic lower bounds towards the end of the talk, I'll be able to say a little more about that. So the big drawback to this model, unfortunately, is that you get significantly lower accuracy. Okay, and we'll see examples of why that is. But basically, we're going to get much stronger lower bounds in this model, and there are sort of very clear reasons for that, information theoretic reasons for that I hope will be clear by the end of the talk. A number of the deployments that were mentioned in earlier this week use this model, though. It's an important model. So the Apple, the differentially private randomization that goes on your smartphone or in your Chrome browser, they both sort of use this local model. And so, understanding this model remains important. And the reason they use it is precisely because they don't want to be on the hook for holding all the data in clear form, sort of in the clear. Okay. And I'll talk more about some open questions as we kind of go through the talk. But one open question that I won't really get to in the talk, but I think is sort of a really cool question for crypto types, of which there are quite a few in this audience, is that if you're the kind of person who likes multi-party computation protocols, then you will quickly observe that getting these sort of advantages of the local model doesn't necessarily require using the local model. A different approach would be to use a cryptographic protocol to distribute this centralized computation over a large set of mutually untrusting devices. Okay? And the problem, of course, is that currently that type of approach to the problem is not sufficiently lightweight for the sort of scale of applications that places like Google and Apple have in mind. But it's not at all inconceivable that it could become, that we could develop protocols that are sufficiently lightweight, even with the technology we have now, with the cryptographic tools we have now, never mind, standard, standard assumptions like I/O, right? Popular assumptions like I/O, right? So that's right. If you assume that, right, all right, okay. I won't go into it. But anyway, so this is like a really, there are some sort of nice open questions here. And offline, if you'd like, if this is your thing, I could try to formulate this question a little more precisely for you to, what I mean by like what we need here, or what would make a big difference here. Okay, but the theme for this talk is to understand this model, what we can and cannot do in this model, and that basically there are going to be two parts of the talk: some stuff we can do and some stuff we can't. Okay, so let's start by revisiting randomized response. So this was the first example of a differentially private algorithm we saw in this winter school when Katrina made us all provide information about whether or not we'd ever cheated on whatever we'd cheat on, exams, right? Yes, Sarah.
A big picture question.
Yep.
So if I'm understanding the definition of the local model correctly, and you're saying that that's the model that's being used with
Yep.
Apple, for example, does that really mean that every person's iPhone is epsilon indistinguishable as far as Apple is concerned?
It means that, no. It means that for the information they're collecting via the protocol,
Sure.
if you were to change that specific piece of information,
Right.
it would not,
But that's actually the case.
yes.
Okay.
Yeah, that is actually the case for both Apple and the Chrome, for iOS and the Chrome browser. That is really the case. Now, of course, iPhones are not indistinguishable from Apple. It's a point of view, or from anybody else's, right? They have different cases. They have, serial numbers, right? They have IP addresses, that kind of thing. Okay. Okay, and so the version I'm giving you, the version I'm giving you is basically the same thing that Katrina presented. I guess, basically, this version comes from this paper of Ducci, Jordan, and Wainwright, but it's not really, it predates them by, 40 years or so. Okay, so maybe 50. So, all right, so again, each person has so simple randomized response, each person has some data, which comes from some domain X, and X might be really big. But now there's some function that an analyst wants to know the average of, right? So the analyst wants to know what fraction of people in this room, for example, have cheated on an exam, and we could, turn that into a function like this by mapping each person's data to 0 if they never cheated on an exam, and 1 if they did cheat on an exam. Okay. And we're going to, so the randomization operator we saw in Katrina's example, we asked each person to flip a coin and basically either report their correct data or report the opposite of their correct data. Okay? And we're going to, this is basically what we're going to do, but I'm going to kind of give it to you in a slightly different form. We're going to rescale things to make the math easier for understanding how to, how to process the answers. And we're going to do it this way. So we're going to assume, for simplicity, that each person's data is either -1 or 1. It turns out by if their data is a value between -1 and 1, you can sort of randomly round it to either -1 or 1 in a way that preserves that has the right expectation, and then use the rounded value in this protocol, and that will work. Okay, and now what we're going to do is the randomization operator on input either -1 or 1 will return one of two values, either C sub epsilon or minus C sub epsilon, where C sub epsilon it's about 1 over epsilon. It's this like weird looking constant. And it'll return, if my data is +1, then I'll return the value plus C sub epsilon with probability a little greater than 1/2, so that's e to the epsilon over the e to the epsilon plus 1. And I'll return minus C epsilon with probability a little less than 1/2, in this case 1 over e to the epsilon plus 1. Okay? And if you sort of just look at these two probabilities, you'll notice that the ratio of the two probabilities is exactly e to the epsilon, so this is going to be differentially private. And if you look at 1 minus these two probabilities, you actually get the same thing. So again, it's okay. It's off by, it is actually differentially private. Okay, and sort of basically the way the value, the person's input comes in is basically you're skewing, if my data is 1, then plus C sub epsilon is a little more likely, and if my data is -1, then minus C sub epsilon is a little more likely. Okay, and it's a sort of a fairly easy computation. You can just check it on your own. That the expectation of this operator, the expectation of the value you output, is exactly your input. Okay, so the reason we've sort of done this rescaling is to make the subsequent computations easier, and the way we've set it up is so that in expectation, what you send to this aggregator is exactly what you put into the box. Okay, but then what you're getting is what the aggregator is actually getting is not not 1 or -1, but rather minus C epsilon or plus C epsilon. Okay, and the reason this form is really nice to work with is that if I want to estimate a proportion, then I can just average the aggregator can simply average the values that were received from the individual people. Okay, and sort of if you think about like what can I say about the accuracy of this process? Well, I know in expectation, just by linearity of expectation, I will get the exact correct answer in expectation. And then, how far from the correct answer will I be? Like, what's the standard deviation of this of the estimator I'm getting? Well, each of the individual responses is between roughly 1 over epsilon and minus 1 over epsilon. And so so if I look at the standard deviation of Q of y, it's going to be at most 1 over epsilon, well, order of anyway. And so the standard, and so what that gives me is sort of that when I average n of these values, averaging reduces the standard deviation by a factor of square root of n, and so the standard deviation of the estimator I get is going to be 1 over epsilon times 1 over square root of n. Okay? And so this sort of gives me a nice clean bound for how accurate my estimate is going to be. It's within plus or minus 1 over square root of n. And just for contrast, if we compare to what we would get in the central model using the Laplace mechanism, sorry for the graffiti, in the central model we get noise 1 over n epsilon instead of 1 over epsilon, so 1 over epsilon n instead of 1 over epsilon square root of n by the Laplace mechanism. And so you see, right away we see this sort of big difference in the accuracy we can get in the two models. Okay. And that difference is unavoidable, as we'll see sort of later in the talk. This bound is as good as you can get it, as it could possibly be.
Adam?
Yeah.
So this is right the original Agrawal paper from, they just added uniform noise, right? They added plus minus some value in the uniform.
Correct. Yeah.
Why is this
Better?
better? Yeah.
So the reason is so if you're sort of comparing, we're comparing like these two density functions, then with some probability you wind up in this area, right? And then you learn exactly which of the two values. So we're looking at so just to be clear, these are density functions centered at say minus 1 and 1. Okay. And if the kind of analogous thing would be to pick that interval to have width 1 over epsilon, and then your probability of winding up in this area would be about epsilon, which means the probability that you learn somebody's data is on the order of about like epsilon n. Or, I mean, in fact, yeah, epsilon n could be bigger than 1, but yeah. Okay. It's like 1 minus epsilon raised to 1 minus epsilon to the n or something. Okay, but anyway, basically with high probability you're going to learn a bunch of people's data exactly. Okay, whereas if you say add Laplace noise to either use this randomization operator, another thing you can do by the way would just be to add Laplace noise to each person's data, but then it's a little messier, your tail bounds get a little like crankier. Yeah, so this is what we want to avoid. And basically this gets exactly the same utility as the uniform noise, but a much stronger privacy guarantee. Okay, so like what can we do with this little randomized, so we've got like a box, right? We've got this thing that, if I give you a function that maps the domain to numbers between minus 1 and 1. In fact, they can be continuous between minus 1 and 1. It doesn't have to be either minus 1 or 1. Then I can accurately estimate the average of that function over the data set. And it turns out that we don't even have to go we don't have to go and invent algorithms that process data this way. It turns out there's like a class of algorithms that interacts with the data this way that are well studied. They're called SQ algorithms, where SQ stands for statistical queries. So again, here each statistical query is a function of this form, and roughly speaking, an SQ algorithm proceeds by asking averages of queries of this form over the data set. Okay. It's actually, in reality, it's a little more complicated. The SQ formalism is normally it's normally formulated in terms of averages over some underlying distribution, and I will sort of ignore that distinction by and large for this talk, although it'll come up quite a bit tomorrow. And you know, this class of algorithms was sort of named by you know, Michael Kearns in his PhD thesis, and it turns out that a huge fraction of sort of basic learning and optimization algorithms can be expressed in this form. Not all, but many. Okay, so in particular, every sequence of k statistical queries can be computed in this local differentially private model with accuracy about, call it, you know, square root of square root of k over n. Okay, and the way you do this is you just you know, if you want to answer a sequence of k queries, you just randomly divide people into k groups of size n over k, and then ask each of the groups to answer one of those questions. Okay, and then so instead of getting 1 over square root of n, you get 1 over square root of n over k, and then you pick up an extra log k factor because the union bound over queries. Okay, but you know, basically what this says is that as long as you've got lots of data, you can run any SQ computation in the local model, and you know, basically it's going to work. Okay, so that's certainly one family of things we can do, and the natural question is to ask, well, what other kinds of things can we do in the local model? Oh yeah, that's in the central model we can do a little better than that. We get more like k over n epsilon. Okay, so every SQ algorithm can be simulated via a locally differentially private protocol, and the natural flip side to that is to ask if every well, there's sort of a couple of questions. Is you know, we can do this with local differential privacy. We can do this with centralized differential privacy. And the natural question is, what kinds of things, you know, can we do things that don't fit into this SQ model, right? Is, like the strongest type of statement one could hope for would be to say that, well, can every centralized differentially private algorithm be simulated by SQ or by local differential privacy? And the answer is no, and one of the reasons passes through this sort of SQ formalism. Okay, so here are 3 statements we do know how to make. First of all, every locally differentially private algorithm can be simulated by an SQ algorithm when data is cheap. So as long as I'm willing to allow a blow up in the amount of data the algorithm uses. Okay, and where I can control exactly what that blow up is, but it's, you know, okay, some very crudely, you know, quadratic or cubic in the original data set size. A second theorem is that there's no SQ algorithm. There are tasks that cannot be done in polynomial time by SQ algorithms. Okay, so it turns out, for example, no SQ algorithm can learn what are called parity functions with polynomially many samples, and specifically what's known, this is also a result of, I guess, Kearns and Valiant or something, I can't remember exactly the attribution, but one requires, for d-dimensional data, you require a data set size that is exponential in d. You need a sample size exponential in d.
How can parity be relevant to differential privacy? I mean, every single value changes the output of the function.
So we're learning, sorry? Repeat the question is, what's the connection, how can parity be relevant to differential privacy? Okay, so, you know, as a theoretical computer scientist, I'm obligated to answer that parity is relevant to everything, and that, you know, like.
How can you do it in differential privacy?
So that's the, well, hold on, that's the next, so let me state this and then I'll answer your question. Okay, so in the centralized differentially private model, you can learn parity with only a linear number of samples in the dimension. Okay. Now, what does it mean to learn parity? I actually am not going to, I was not planning to define it carefully. It'll come up in, I just mean, there's, you know, here's this task you can do. It doesn't matter that it's called learning parity. We could call it, you know, polishing shoes, right? It's not the, so what it is, it's asking if, if each person's data is a binary vector together with like a label saying whether or not, you know, they're blue people or red people, you want to know, is there a parity function that generally predicts well whether or not people are blue or red based on their binary data? So you're not taking a parity across people in the data set, you're taking a parity across attributes in the data set. But as I said, I'm not going to define what learning parity is in any formal way. Kobe will tomorrow. All I want to the thing that you can get without knowing what learning parity means, we can still interpret these three results in the following way. What they tell us is that, so the first theorem basically says that, you know, as long as we don't really care about, you know, as long as we're not asking what can be done with a very specific value of n, but like what problems can be solved with polynomial amounts of data, then local differentially private, problems that are solved locally differentially privately and problems that are solved by SQ algorithms, those are the same thing. They're the same class of problems. The second theorem says that there's a problem, you know, outside of this green blob, namely learning parity. And the final theorem says that that problem lies inside of the gray blob. And so these bubbles are actually really distinct. Okay. So this is sort of the first kind of global picture we can paint of the sort of the power of locally differentially private algorithms. And of course, it's natural to ask, okay, so you know we've separated these two models. We kind of have a characterization of local differential privacy. Are we done yet? So this characterization dates back to 2008, a paper of Kashi Vishwanathan, Lee, Kobe Nissim, Sofia Rasodnikova, and myself. So one might ask if it's over. You know, is the story over? But of course, you know, it's not, because you know, it turns out in practice these pesky polynomial factors really matter. You know, there's a big difference between linear in n and quadratic in n. And so, you know, we're actually going to have to work pretty hard to understand more precisely what's going on. All right. So, outline for the rest of the talk, I'll tell you about some of the stuff we can do in the model and some stuff we cannot do in the model. And in particular, I'll try to sketch the relation, I'll give you the main idea of the relationship between local differentially private algorithms and this SQ model, and also the role of information theoretic lower bounds that I mentioned earlier. And on the positive side, I'll talk about a problem that is kind of interesting, this sort of what's called the heavy hitters problem, or which is basically a histograms problem, and that illustrates, you know, some of the things that one can do. Okay, so let's start with the good news. Okay, so histograms in the local differentially private model actually have been studied a lot. You know, I guess not surprisingly, you know, constructing histograms is just a very basic problem. So again, what's our model? Every participant has a value that's a number between 1 and d, which corresponds to, you know, which bin they fall into. And the histogram is simply the vector of counts for those bins. So n sub j is the number of people whose value is exactly j, or people in the jth bin. Okay. So how can we try to compute histograms in the local model? So we know how to do it we talked a lot about it in the centralized differentially private model earlier this morning. Let's see how we could do it in the local model. Well, one simple way would be to basically use some kind of, you know, straightforward noise addition, kind of like what we started with in the central model. So a nice way to think about this is I'm going to take each person's data xi, and I'm going to map it to an indicator vector, e sub xi. So that's the vector it's a vector of length d that has a 1 in position xi and 0 in all other positions. Okay. And now to randomize my data, what I'm going to do is I'm going to take that. So now I've got, you know, bits, right? So that looks more like what I already know how to deal with using randomized response. So I'm going to take my basic randomized response operator that we saw a minute ago, and I'm going to just apply that entry by entry to my vector. Okay, so I'll get a new vector. We'll call it q prime of xi, and q prime is a vector of length d with entries that are, you know, essentially plus or minus 1 over epsilon. Okay. Now, the reason this is sort of a useful way to think about it is that the histogram I ultimately care about, it's just the sum of these indicator vectors, right? And so I've randomized things in a way that preserves expectations, and so a natural way to aggregate these vectors is simply to average them out, or to add them up, rather. Okay? And using exactly the analysis we had on the previous slide, one can show that the kind of the expectation of the L infinity difference between the vector of histogram counts we estimate in this way and the vector of true histogram counts is going to be on the order of square root of n, and we're going to pick up an extra factor of log d because of the union bound over the d entries of this vector, and then we get this over epsilon. Okay, so so this is like a nice clean way to to think about approaching this problem. Contrast this with what we could get in the central model, which was where there was no dependency on n or d. And it's sort of clear that we're not doing as well as we could have before. But we're getting the benefit of distribution. And sort of, again, this leads to the question of whether or not, is this simple noise addition protocol the best one possible? Because in the central model, it wasn't, right? In the central model, we were able to do better. But unfortunately, here, this is really the best you can do. This is the optimal noise bound. This noise bound is as good as you can get for this problem, okay, in the local model. So, so simple noise addition actually works really well, meaning as well as as one could hope for in this model. All right. So. This is a relatively simple way to approach the problem. Maybe what's less clear is like, okay, so, can we just stop here? Are we done with histograms? Right. Maybe. I told you this is the optimal error. Is there anything like anything else we might want from the protocol that this particular version, can you see any drawbacks to this protocol? Kahmit? Yeah, the running time here is going to be and the communication is going to be very large. So in order to execute this protocol, I need to randomize every entry of this indicator vector explicitly, and that is going to take me time order of d. Then I have to send this like gigantic thing over to my aggregator, and my aggregator has to hang on to it, right? The aggregator has to keep, at least naively, keep until the end of the protocol this whole vector. Uh-oh. No, we don't want that. Okay, Kobe to the rescue. All right. So, for example, the way it's used, tens of thousands. Oh, really? Yeah. So it could be, for example, words, like, words in a dictionary. Do I have power?
I think it's on the floor, maybe?
This is plugged into something. Here we go. Right. The number goes up the more degrees they have. Okay. So okay. So this is so one thing that this does not provide, and that we could hope for, is succinctness and efficiency, right? So so this has optimal error, but the problem is the communication and the server-side storage is order of d, and so what we might ask, well, how much space is really needed for this problem? Okay. And it turns out the answer is, actually I could have put a theta on this, it's really very neat that the exact space bound that you need for the server for this problem is exactly is epsilon times n squared of log d. And just to give you a sense of where that comes from, So this is, by the way, this is work done at Apple, and this is a citation to a patent because they don't actually publish what they do, but you know, they do file patents, so you know, this stuff comes up. Okay. No, it's amazing how few lower bounds are proven, have been proven in patents historically. Okay, but the lower bound, it turns out, is like trivial here. So let me just explain the lower bound for at least when D is large. It's sort of. By the way, this bound is for when D is significantly larger than N. If D and N are comparable, it's a little more complicated state. It's more like log of N choose D or something. Okay, so D choose N. So anyway, when D is large, it's easy to see what's going on. If you want to solve the histogram problem to this level of accuracy, then at the very least what you have to do is remember all the bins whose counts are larger than this. Okay, how many such bins are there? Well, there could be as many as, you know, epsilon times square root of n over log d, which is, so it's like n divided by this number. Okay, so you can have, you know, you have to store all the elements with at least, sorry, this is not, sorry, this is not quite, what it says on the slide is, you know, forget what I wrote on the slide, let's just listen, right? So this number is the number of bins you must store. That's the number of bins whose counts could be above threshold that you would have to keep around in order to solve the problem in any form. And if you multiply that number by log d, what you get is, which is the number of bits it takes to represent the name of a bin, then what you get is exactly this space bound. Okay? So you're not going to be able, just to like store the answer, you need this much information. So you're not going to, it's not going to get any better than that. And what's kind of cool is you can match that. And the way you do this, sort of building on an idea that's had appeared in a few papers previously, which is this sort of connection to algorithms from the streaming literature for a problem that they call heavy hitters, which is basically histograms. And specifically, the way you get this noise bound is by adapting the count min sketch of Kormod and Muthukrishnan. Okay, and so I can explain to you just very briefly how this works. So just to sort of understand what we're getting before we get into the construction, what we're getting is not, at least on our first pass, what we're getting is not sort of an explicit representation of the histogram, the way we'd normally think about it. What we're going to get is a data structure that allows us, for any bin j, to estimate the number of elements in bin j. Okay? And if I want to construct a histogram, I can do that by just explicitly querying the name of every single bin. Okay? But of course, that takes time. That might take time. So this solution is not going to, the construction of this data structure is actually going to run in time, only logarithmic in d. So it only takes time order of d if you really want the explicit whole histogram. Okay, so the idea is we're going to select a bunch of hash functions from our data set that map our data set into a smaller set, not our data set, but our universe into a smaller universe. And the exact size of the universe doesn't really matter, but call it square root of n. And then what we're going to do is we're going to sort of divide our users randomly into k groups. Okay? And we're going to ask each group to help construct a histogram for the hash of their value for, under the first group will construct a hash of their value under, the first hash function, the histogram of their value under the first hash function. The mth group will help together construct a histogram for the mth hash function, and then the kth group for the kth hash function. Okay. So now what happens is, they'll do this using the protocol we saw before, but now notice that they're not working over, here the communication isn't on the order of d, it's on the order of square root of n. In fact, a little less than that. Okay. What the aggregator stores these k histograms. Okay. And when someone comes along and says, hey, I want to know how many people were in bin J, what the aggregator will do is it'll get kind of an estimated count, sorry, not for J, but for, for the hash of J. Okay, so each of these guys will give me, sorry, I'm not used to this machine, so I'll get it. Okay, so each of these will give me some estimated count for bin J. Okay, we'll call these estimates C1 through C hat 1 through C hat K. And then we'll take the median of these estimates, and that's going to be our output. Okay, for our estimate for the frequency of item J, the count of item J. Okay, and the reason this works is that, so in the normal streaming setting, these are exact histograms, and you take the minimum, not the median. But in this setting, we've got sort of noise, and so it turns out the median is a better solution. But the basic idea is each of the counts for each of these histograms is an overestimate of the count in the original data in the whole data set, because this hash function could collapse several histogram bins together. Okay, but the parameters are selected such that in any given execution of this little protocol, there's a constant probability that the bin you care about is basically all alone or close to all alone in its in its like hash preimage, and so at least one of these, a constant fraction of these will not be like drastic overestimates. A constant fraction of them will be actually pretty good estimates. And by taking the median, if that constant fraction is like bigger than 2/3, then by taking the median, we will sort of pick out that good estimate. Okay, and so this is the basic idea. I'm not going to go through the whole analysis, but this is the basic idea. And once you've got the sort of this level of analysis, this level of description, then doing the actual analysis is just sort of standard tools. Okay, but this is an example of how you can do it, and it turns out this construction basically achieves this exactly optimal space bound that we had on the previous slide. Okay, so that gives us this sort of nice, clean data structure for where I can query the count in any bin, of course, it doesn't totally solve the problem, because what we really want is not like we don't just want this data structure. What we want is the list of large bins, right? We want the list of things that I should actually care about. I don't want to have to like explicitly look at all these many bin counts, right? So an explicit querying process is going to take me order of d time, which is not necessarily practical. D could be, so as I said, in practice, often D is in the tens of thousands, in which case this order of D is fine. It's not a big deal. But actually, these protocols continue to work with D in the millions and even in the billions, because the error guarantees are only logarithmic in D. And there, at some point, you run into this region where it's impractical to explicitly do all these queries. Okay. So it turns out that there are protocols that get this additional property of being time efficient also, meaning that what you really get is like a list of the heavy bins and not just a data structure for estimating the frequency of any given bin. So there's a protocol based on some sort of error correcting codes and hashing ideas in a paper of mine with Raif Basili. And 12 years previously, what I now consider to be a better idea to Kormod and Muthukrishnan, which is sort of, in the context of this particular problem, was suggested to us by Frank McSherry, thus realizing Aberdeen's Thakurta's generalization that all unattributed heuristics are probably due to Frank McSherry. So this one's now attributed. It's really due to Frank McSherry in this context. Anyway, it gets a slightly worse error than the protocol, at least asymptotically, than the protocol in this paper, but it's much lower space and it's probably more practical. Okay. One open question I'll mention, so I didn't specify these results at a level of precision to make it clear what I mean by this, but these protocols do trade off a little bit of error. They add there's these polylog factors that get thrown in to get time efficiency. And so it's still an open question of whether or not you can actually recover the exactly optimal error and keep essentially optimal space and also have time efficiency. So that I don't know how to do. And it matters. So basically, maybe something I didn't mention is the thing that Google and Apple do, it's all histograms. Like currently, everything they implement is doing one form or another of this basic task. They're not doing anything really fancy yet. So better protocols for these problems actually, will have a reasonable chance of like winding up on the device in your pocket within a time scale of months. Okay, that said, that there do exist local protocols for other things. So as I said, anything you can do in the SQ model, you can do in the local model. There are some particularly nice protocols for estimating averages of vectors under various assumptions about the vectors. So some useful these are from this paper of Ducci, Jordan, Wainwright that I mentioned earlier. So one specific case that's interesting is when I'm estimating a histogram on a relatively small universe, and what I'm trying to optimize for is L1 error, not L infinity error. Another interesting case is L2 bounded vectors, and that one's on the problem set that we'll look at in a little bit. There's some nice protocols for convex optimization via gradient descent and other techniques that I'll mention tomorrow. And then there's I didn't have time to pull together all the citations, but there are some nice, relatively recent papers on sort of what I'll call selection problems. So this is like finding the most liked Facebook page that Katrina talked about, or what is slightly more practical in the local model is finding the most liked Facebook page under the restriction that each user only gets to like a bounded number of pages. And then with that additional restriction, you can actually do useful things in the local model. Okay, so that's sort of just a quick picture of some of the techniques that can help us construct local protocols. I now want to tell you a little bit about the stuff we can't do, because I think it's also, of course, interesting to understand. So, the first result about things we can't do comes by this connection to SQ algorithms, and like many sort of complexity results, it's actually a positive statement. What we're saying is that SQ algorithms can simulate locally differentially private protocols. So that's going to be an algorithmic statement. But what that means is anything that you can prove is impossible to solve using an SQ algorithm will, by implication, be impossible to solve using local differential privacy. Okay. So, I'm not going to formulate the exact statement, but, very crudely, every locally differentially private algorithm with n data points can be simulated by an SQ algorithm with some related number of data points, roughly n cubed. To nail this statement down precisely, it's really a distributional statement. You assume that the data are drawn IID from some distribution, and you talk about how the algorithms relate to that distribution. So it's I'm just not going to get into the level of detail, but you can probably reconstruct the statement if you sort of think about it for a few minutes. Okay, what I will tell you about is sort of the idea that goes into it. And the key piece of this theorem is to somehow, we're going to take a locally differentially private randomizer, and we're going to transform it to have some simpler form. And post-transformation, it'll be more obvious how we could try to simulate queries to this local randomizer via statistical queries. Okay, so here's the basic idea. so here's our, let's say we've got some randomizer, we'll call it R. So it doesn't have to be the randomizers we were talking about earlier in the talk. It's just anything that's locally differentially private. Okay, so in the normal picture, the participant, puts in a value x and sends R of x to the aggregator, where R of x is a random variable distributed, where the randomness comes from the coins of R. Okay, so we're going to transform it into a new protocol, and the new protocol is going to have the following form. So what the aggregator is going to do, first the aggregator is going to do something. The aggregator is going to sample an output of this randomizer with some default input. Let's call it 0. Okay. And let's call it, so the aggregator samples some value, gets a string, let's call it z, and the aggregator is going to send the participant z, and the participant is just going to respond with a bit that's selected randomly, according to a specific distribution using the randomizer, basically telling the aggregator whether or not to use this value z or to ignore this participant. Okay? So this is it's a special case of what's called rejection sampling. So I want to sample from the distribution R of x, but what the aggregator is going to do is sample from R of 0 and then have the participant help him decide whether or not to keep this value or throw it out. Okay, and the result is there's an epsilon differentially private randomizer R prime such that for every x, when the output of the randomizer, when the output B of the randomizer is 1, then the thing that the aggregator keeps, the distribution on the thing that the aggregator keeps is exactly R of x. So it's distributed exactly in the correct way. And on the other hand, the probability that the probability for every x, the probability over all z that the aggregator keeps something is exactly a half. Okay. So if we were to take a protocol that was based on the randomizer R and replace it on based on the randomizer R prime, we would get a protocol that lowers the communication from the participant to the aggregator down to a single bit per randomization I want to do. Okay, so that's kind of fun, it lowers communication, at least in one direction. The downside is you end up randomly dropping half of your data, right? And that seems kind of like a big deal, but actually if you sort of look at the additional error introduced by that step, that's generally going to be negligible compared to various other sources of randomization in this sort of whole process. So this is actually not that big a deal. And furthermore, for all the randomization operators I've ever seen, you can kind of get the same effect without you can actually get the probability, you can sort of modify this process and actually have it work with probability 1 instead of probability a half. And maybe, so the last thing that might be questionable about this thing is that, we haven't really reduced the communication down to 1 bit, because we've got all this communication going the other way, right, from the aggregator to the participant. But actually, it turns out that's not that big a deal, and that's because, in fact, the aggregator doesn't really need to send z. The participant can generate, because because this value z, the way it's generated doesn't affect privacy. It only affects sort of the ultimate utility guarantee. What the aggregator can do, it can just broadcast to all participants the seed of a pseudorandom generator and ask all participants to generate z on their own. Okay, and with an appropriate pseudorandom generator, this will work just fine. And it's not, you don't need like computational assumptions even for it. Although that's the natural way to think about it. But the point is that anyway, the way z is chosen doesn't affect the privacy guarantee. So the privacy guarantee will hold no matter what. And as long as you get a reasonable pseudorandom generator, then you'll still get this sort of distributional guarantee on the output that you want. Okay, so how does this randomizer work? Let me explain it. It's actually very simple. So given on inputs x and z, what R prime is going to do, it's going to compute a probability. So the first thing it's going to do is going to take the ratio of the probability that R of x equals z over the probability that R of 0 equals z. And it'll then multiply that ratio by a half. Okay. And it will return b equals 1 with probability exactly p sub xz. I should mention that this version requires epsilon to be bounded above by like 0.6 or something. And you can, if your epsilon happened to be bigger than that, you can tweak it. And the only reason you need an upper bound on epsilon is so that this number p is not greater than 1. Okay, so what's going on? Notice, let's look. So notice that this quantity pxz we compute, it's always, because it's the ratio of two, the probability of generating z under two different inputs by the original randomizer r, it's always between e to the minus epsilon and e to the plus epsilon over 2. And so, in particular, it is epsilon differentially private. Like the dependency of the probability that I output 1 and the number x is limited to this sort of range of ratios. So it's always epsilon differentially private. And now if I look, what's the probability that I select the value z via this process and I keep it? Then it's the probability that I selected z, that's the probability of r0 equals z, times this pxz, so that's 1/2 times the ratio. And now two of these probabilities cancel, and you're just left with 1/2 times the probability that rx equals z. Okay, and so conditioned on the event b. So the important thing to notice here is that it's proportional to the probability we wanted. Okay, so when we condition on the event b equals 1, it remains proportional to the thing we wanted, and so it's actually the exact correct distribution. Okay, and the other thing you can notice is that if you sum over all z, then you get 1/2, so the probability that b equals 1 is at 1/2, and z is correctly distributed. And an important but somewhat subtle point is that the probability that the protocol works is the same regardless of x. So the fact that the protocol works doesn't leak information about x. Okay, so that's it. That's how it works. Okay, so this is sort of a simple transformation that'll massage my original randomizer into one where all I have to do is send 1 bit to the aggregator. Okay, and so why did we jump into this whole transformation? We said our original motivation was connections to SQ. The way we can use an SQ query is to evaluate, rather than evaluating just one probability. So what I'll do is I'll pick one value of z and I'll give the same value of z, sort of roughly speaking, I'm giving the same value of z to many different people, and rather than just computing one probability pxi sub z, comma z, I'll compute the average of this probability over a large set of data points. Okay, and then if I use that average to do this sort of this rejection sampling trick, then when the data are drawn IID from some underlying distribution P, then we can actually sample from the correct distribution that I would get by picking a fresh sample from P and running it through the randomizer. So what we can do with SQ queries, if the data set has samples drawn from P, we can basically simulate the way the randomizer would behave on a fresh random sample from P, and that's good enough to simulate the action of the locally differentially private protocol. Okay, so this allows us to kind of simulate the entire locally differentially private protocol, and that gives us the result that I didn't state precisely, but that I kind of gave you the flavor of. Okay, so that gives us this sort of picture. Any questions about that? So I'll wrap up with just another kind of another tool for understanding the limitations of these locally differentially private protocols. And whereas this sort of connection to SQ gave us this very broad strokes characterization of what is doable, this sort of more information theoretic approach will allow us to prove finer grained lower bounds on accuracy. So as is the case with epsilon 0 differential privacy, lower bounds for epsilon delta, there's an L missing there. That's actually sort of semantically important here. Lower bounds for epsilon delta local differential privacy are relatively easy to prove via packing arguments of the kind that John outlined. For local algorithms, it turns out it's worth doing a little more effort to put these packing arguments in a kind of information theoretic framework, and that allows us to get like a sort of a cleaner version of the arguments. Whereas for epsilon zero differential privacy, you can do the same thing, but it doesn't really buy you anything. It doesn't buy you any simplicity, so we don't do it. And this is sort of this information theoretic framework. Is implicit in a sort of a lower bound in a paper of Baimel, Nassim, and Omri, and also sort of later was kind of made explicit by this paper of Ducci, Jordan, and Wainwright, and generalized in another paper. Anyway. Okay, so the basic idea is that we're going to suppose that there's some distribution that's generating our data set. So the points in the data set are generated IID from some distribution. And what we're going to try to understand is how much information the protocol leaks about the distribution. So we don't really care about the data per se, we care about the distribution that generated the data. But of course we're going to go via the data. Okay, so pictorially, here's P. Here are my data points. Now these are going to be randomized, not necessarily using the same randomizer, but using some collection of randomizers. And then they're fed to the aggregator who produces some output. And what I'm interested in is how much information the output leaks about this input distribution. Okay, and the basic lemma that makes this type of analysis possible is the following. If I just look at one person's data and its randomization, the number of bits of information that are revealed about X by R of X is bounded by some constant times epsilon squared. Okay, so that's going to be like the basic lemma that we're going to use. You look skeptical.
What's that?
You look skeptical. No, okay.
I mentioned it in yesterday.
Oh, yeah, okay. So maybe I wait in the composition talk. Okay, good. In that case, sorry, I should have known that. So I don't need to prove it. Did you prove it?
For randomized response.
Ah, okay. Good. So it holds more generally. I was going to prove it more generally, but you know what? We'll skip it. Okay. So here's so you can prove this statement in general, and it goes by some bound on the Kale divergence between distributions that are close in this sort of sense of epsilon differential privacy. But we're actually going to use what we're really going to want is a slightly strengthened version of this lemma, which is that if I've got a randomizer that's epsilon differentially private and an additional process that sort of takes an input and ignores it with probability 1 minus alpha and keeps it with probability alpha, then if I compose the randomizer with this additional erasure process, then the mutual information goes down by a factor of alpha squared, where alpha is the probability of keeping the value x. And somehow this alpha squared, this is really what matters. So this is the thing that'll give us the square root of n scaling in our error bounds later. Okay, and the proof of this statement, I'm also not going to prove it, but the way you prove this statement is by showing that the composition of R and W is order of alpha times epsilon differentially private. So did anybody mention the sampling? Okay, so this is true. You can prove it relatively easily. It's a calculation. It's not very hard. Okay, so again, the thing we want to remember is that the mutual information between the input to one of these little randomization boxes and its output is really small. It's on the order of alpha squared epsilon squared. Okay, so now suppose we want to bound information about the whole process. You know, we now want to understand the whole process, right? So we've got, so we're going to imagine the following thing. We're going to sample some value, special value v from a distribution, and we're going to consider a data set that consists entirely of copies of v. Okay? And now we'll look, the zi's will be the effect of running the randomizer, and that the randomizer can depend on I, that's fine, on each of the data points. And what we're interested in is the mutual information between v and this set of outputs. Okay? And the reason we can bound that is because so here's our picture, right? So by the okay, so at this point I'm going to sort of assume some familiarity with information theory. If you haven't seen these statements before, you can just take them on faith. But you know, we're not going to use anything like really complicated. So it turns out that the usual notion of mutual information admits something called the chain rule. That gives us the following statement, which is the mutual information between v and the collection of the zi's is at most the sum of the mutual information between v and one of each of the zi's individually, conditioned on the past zi's. Okay, so there's some conditioning statement. But because of the particular structure we have here, the conditioning step doesn't actually change the mutual information. Sorry. And so this is actually equal to the sum of the mutual information between leaked by each of the points individually. And now, you know, once I have this statement, then this is at most, because v is equal to xi in this particularly simple case, this is equal to this is equal to the mutual information between x and z, its output, its corresponding output, and as we just said, each of those terms is bounded by epsilon squared, so the whole sum is bounded by n epsilon squared. Okay. And so what this all means is that the number of bits of information about the output that are leaked about the input leaked by the output is at most epsilon squared times n. Like I guess, you know, if you chose the input distribution differently, this analysis wouldn't necessarily work. But for this particular type of input distribution, it works. So now we can ask, you know, how can we use this? Well, let's use it to show that our histograms are as good as they could be. Okay. So each participant has, again, you know, this is just a reminder of what's going on. Each participant has a number between 1 and d, and you want to know the approximate histogram of these values. So what we're going to do, we're going to construct a data set by picking a random value between 1 and d, picking a single bin, and putting everybody in that bin, right? And now any like remotely reasonable histogram algorithm had better tell me v, right? Because obviously, like, if all my data points are in one bin, I better be able to, and I can't find that bin, you know, things are not going well. All right. So, you know, it should work with high probability, and there's a standard way to relate sort of high probability equality with mutual information, called Phantos Inequality, that says that in this case the mutual information between A and V has to be at least you know, log of D, the number of bits of information in V. And now we can just sort of combine this with the thing we knew before, that the mutual information between V and A is at most epsilon squared of n. epsilon squared n, and so log d is less than or equal to epsilon squared of n, epsilon squared n. And so what we conclude is that in order to get non-trivial error, I need at least log of d over epsilon squared samples. Okay, so this is sort of our first lower bound. And this shows us a couple of things, but maybe the most important one is it shows us that some dependency, unlike in the central case where I have these, where I could get away without any dependency on the domain, here I really need a dependency on the domain. Something I didn't mention, I should have, actually, sorry, let me just go quickly back to this slide. This lemma basically continues to hold even with epsilon delta differential privacy. You pick up an extra term of about delta log d. And it turns out that in the parameters are such in the context we care about where this delta log d isn't going to change anything. Okay, so unlike in the central case, here the information theoretic proofs actually tell me something about epsilon delta version of the definition. And so anyway, so what this argument gives us is that the upper bound we had of square root of log d over epsilon squared n is sort of tight for the range where the error is just going from sort of trivial error to non-trivial error. So it tells us that the upper bound, we don't know that the upper bound is tight everywhere, but we know that it's non-trivial whenever it could be, which is already like a good start. Okay. But the question maybe we're really curious about is where does this square root come from? Why is that the right thing? Where does that come from? And there we need to sort of handle subconstant error. So there we're going to start off with the same setup. We're going to pick a data set, pick a value uniformly, pick a bin uniformly. But what we're going to do is we're going to consider some new data set, which is not all v's, but it's an alpha fraction of v's, and a 1 minus alpha fraction of just some default value, 0. But it turns out to be important that this alpha fraction is distributed randomly in the data set. Okay, if you don't distribute it randomly in the data set, you get a different bound, a weaker bound. It's just like the bound really doesn't hold. One way to distribute it randomly in the data set is to just like run it through this erasure operator W we talked about earlier, where you keep V with probability alpha and you replace it with 0 with probability 1 minus alpha. Okay. So now you've got a data set with about alpha times n copies of V and then a bunch of zeros. And again, any histogram algorithm or algorithm for the mode that works with probability alpha over 2, that has error about alpha less than alpha over 2 should output V again with high probability. And so now we're basically done. If we think about what is being the sort of view that the algorithm A has of this data set. Right, it's getting, so here, here's V over here. V is being passed through the composition of W and R before being sent to A. And again, the R's can vary. That's fine. And so what matters is like how many bits are leaked by the composition of W and R, and that it turns out this is the stronger lemma that we had on the previous slide. By the way, this lemma is not named after someone named Stronger. It's just stronger. The stronger lemma gives us this alpha squared dependency, and so we pick up a factor of alpha squared in our lower bound. So now log d has to be at least alpha squared epsilon squared to n. And then now when we solve for alpha, we get the thing we want. Okay, so that's all I wanted to say about it. So that's like an example of the application of this bound to histograms. And it turns out that this sort of same bound gives us tight, the same approach gives us tight lower bounds for like a bunch of sort of relatively straightforward statistical problems and even some less straightforward ones. Okay, so I told you about some stuff we can do. I told you about some stuff we can't. Yeah, just wrapping up. So the deployments we know use this local model. So it is, at least for the foreseeable future, an important thing to understand and continue to look at. There are a number of open questions. As I said, there's some open questions related to MPC protocols that basically have to do with getting rid of the local model, which would be great. But there are also some questions about, if we're stuck with the local model, what the power of interaction is in this model, the back and forth between the aggregator and the individuals. And I'll mention a little bit about that in a talk tomorrow. And maybe a really sort of broader question here is what kind of interesting things can we do in this model? So right now, I would say the protocols that exist for the model are significantly less sophisticated than those that exist for the centralized model. That's partly because the design space is more restricted and there are just fewer things you can do. But it would be cool to see more examples. Okay, I'll stop there. Thanks.